Can you hear also me?
Yes, that worked.
Hello.
All right, great. Okay, then we can start the session. Welcome to slot F2. We will have 6 papers to discuss, and the first one is by Kavita. So you're welcome to share your screen and give us a short reminder of your work.
Thank you. Hi, my paper is on popular matchings with one-sided bias. Our input is a bipartite graph where every vertex has a strict ranking of its neighbors. 1 denotes top choice neighbor, 2 denotes second choice neighbor, and so on. This is a well-studied model used in many two-sided matching markets. What one usually seeks in such an instance is a stable matching. Stable matchings always exist, and Gale-Shapley algorithm finds one in linear time. Here we consider a more relaxed notion called popularity. Any pair of matchings can be compared by holding an election between them where every vertex votes for whichever matching it prefers. So let's hold an election between the red and blue matchings. The top 2 vertices abstain from voting because they're indifferent between the 2 matchings. The 2 middle vertices vote for the red matching and the 2 bottom vertices vote for the blue matching. So this election is a tie. Let's hold one more election between the red and green matchings. The red matching gets 4 votes while the green matching gets only 2 votes. So the red matching wins this election, and we say the red matching is more popular than the green one. A matching is popular if there is no more popular matching. So a popular matching never loses an election to any matching. In fact, this notion was proposed many years ago by Garden Force. A popular matching treats all vertices equally. However, in many applications, vertices on one side of the bipartite graph are more important, say while matching students and advisors. We would like to give preferences of students higher priority. A relevant notion here is apopularity, where it's only vertices in the set A who get to cast votes. A matching M is apopular if it never loses an election, where we only count votes of vertices in A. Apopular matchings need not always exist, and there is a simple linear time algorithm to find one if it exists. Here, in fact, all vertices have preferences. So we would like a popular matching, but we also want to show bias towards the side A. So we want a matching that's both popular and apopular. The question we ask is, does the given instance G have such a matching? And our result is a linear time algorithm to solve this problem. We use the machinery of stable matchings. We construct a new graph H such that every stable matching in H maps to a popular half-integral matching in G. However, what we want is an integral matching, moreover, a popular matching that's also apopular. So we need a special stable matching with special structure. And the paper is on such matchings and how to find one efficiently. Thank you.
Thank you very much. So do we have a question from the audience directly? Otherwise, I believe we also have a question in Slack, which is regarding the complexity of the algorithm for fully popular matching problems. Does each while loop iteration take linear time? Is there an upper bound on the number of iterations? I guess that's specific.
So I guess this is a rather technical question.
So if we have a more general question before. Otherwise, I would say just answer it anyway.
Yeah, so in the while loop, basically, I mean, it's linear in the number of edges. So I really don't have the paper in front of me now. But in the while loop, whenever we mm, basically eliminate some edges, every edge pays for its own elimination. And so it is linear in the number of edges.
Okay, then maybe let me ask something fairly general. So,
Sure.
I mean, you have shown that there's another class of popular matching that is polynomial time tractable. So do you think or what is the next subclass of popular matchings that you are going to attack with the hope of finding some polynomial algorithm? Or do you think this is all?
Yeah, so I don't know, but it is a little, there are too many hardness results here. There seem to be too few positive results. Indeed.
That
So
was
when I
my
started
question,
this
yeah.
problem, I really hoped this also wouldn't turn out to be NP hard, and thankfully it was not.
Okay. Do we have any further questions?
So maybe I'll ask. I'm not sure if if the second half of the detailed question was answered. So you said that it's linear in the number of edges, but did you say, or is the number of iterations bounded by the number of edges, or what's the bound on the number of iterations?
Oh, you're right. We forgot that. So the part, is there an upper bound on the number of iterations?
So I really don't have the code in front of me, but I don't think we can bound the number of iterations of the while loop. It's basically the total number of edges. The entire running time of the algorithm is bounded by the number of edges. So, so I remember now, in the while loop, I ask, is there a vertex that's in both some kind of this set and that set? And in case there is one, then in fact, we have to promote many vertices. And so we have to eliminate certain rotations in the stable matchings and so on and so forth. So I don't think I can bound the number of while loop iterations.
Okay,
I'll have to
thanks.
look at it more carefully before answering, but my first guess is no.
Martin, did you want to add something? By the way, these questions were by Zong Gao. I think I forgot to say that when I read them.
Sure, thanks.
Okay. Any further discussion on the paper?
Maybe I have a question, if that's okay. So I was wondering, could you maybe do a hierarchy of groups? So, so in the sense you give A's preferences more weight in this model, but you could also subdivide both sides even further.
Indeed, indeed, sure. That's a very nice question. I need to, probably that's a future research plan. Thank you.
Okay, thanks a lot.
Thank you.
All right, I just wait a second. If there are no further questions, then we can continue with the second paper, which was presented by Jacob Cooper, but the Q&A will be done. Now I lost your picture. Where are you? By Martin Kautecki. There you are. So please give us a short reminder of your paper.
Yes, thank you. Thank you all for coming. So the paper is called Matrices of Optimal Tree Depth and Row-Invariant Parameterized Algorithm for Integer Programming. It's by myself with my co-authors from Monash University, University of Warwick, and Maastricht University. And I'll motivate it from two sides. One is more practical and one is more maybe theoretical. Okay, let me just try to get it to a better, okay, this is better, yes. So this is the practical motivation. So we're interested in integer programming, which is to minimize some objective function over a set of linear equality constraints with lower and upper bounds. And obviously the solution vector is required to be integer. And there's a stream of research stretching back to the 70s, which is interested in detecting bordered block diagonal form of A, which is basically what you see on the left, where you kind of structure the matrix so that it has some border, which is the bottom part, and then it has some blocks along the diagonal. So on the right, you have the original matrix, which doesn't have any parent structure, and on the left, you have the structured matrix. And here, detecting means permuting the rows so that this bordered block diagonal structure appears. And the interest is because solving a matrix structured like this is much easier. So what we do is that we take it one step further, and instead of just permuting the rows, we consider elementary row operations. So when you look at the matrices on the bottom, for us, these matrices are equivalent because taking one or the other as the constraint matrix of an integer program doesn't change the set of feasible solutions. So we're interested in kind of uncovering a sparse bordered block diagonal structure in a matrix. So that's one side. The other side is more theoretical. Maybe you're familiar with the notion of tree depth. So you can consider the dual tree depth of a matrix. This depends only on the structure of non-zeros. But I just defined what it means that two matrices are equivalent. You can go from one to the other by row operations. And so you can define the optimal dual tree depth, which is just go over all the equivalent matrices and pick the one with the smallest tree depth. So this is well defined. And our main result is this is actually equal to the branch depth of a matrix A, or more precisely, the column matroid of the matrix A. And we give a fixed parameter tractable algorithm to compute a depth decomposition, which is the thing that you need to actually transform the matrix to find a witness of this equivalence. So that's our main result, that we can actually detect this structure, which is hidden by some row operations. And some open problems, you can easily define optimal primal tree depth, which is the primal tree depth is just the dual tree depth of the transpose of the matrix. And we don't really have any idea what this optimal primal tree depth is. We know it's not the branch depth of the transpose of the matrix. Another question is to compute this branch depth or the depth decomposition faster. We do it in FPT time, but the complexity is not so nice. And a third question is, I would be very interested in seeing what is actually the branch depth of some instances that appear in practice. There's a very mature benchmark library called MIPLib. And so it would be very interesting to see what is the gap between branch depth and the tree depth of the MIPLib instances. So that's my short take on the paper.
Thank you very much. Then, who has a question? Just unmute yourself. Oh, there's a question from Slack also.
Yes, hi. Yeah, so my question is about the application of this result, for example, in scheduling. So because some of the previous IAP results were motivated by certain applications, that certain applications lead to IAPs of a specific form. Now, do you know or can you imagine some kind of structure or some setting where results of this form would be useful?
Mm-hmm. Thanks for the question. So in all the previous applications that we had of these techniques, the structure was already apparent. So the matrices that we came up with already had small tree depth. I think I guess at this point I can't think of maybe what you have in mind is that there would be a model that we can show, oh, this has small branch depth, but it doesn't obviously have small tree depth. I don't think this would happen because I think that kind of small tree depth models are natural for some problems. Although there are some types of constraints which are natural to write in both ways, and one of them is sparse and the other is not. So really, I think it's going to be more of the third bullet point, that this would be interesting to look at for practical instances, because people from the IP or OR community might be writing models that are not optimal, and this could be some pre-processing step for an IP solver to kind of sparsify the input matrix before running whatever is being run now. That's my guess.
Thanks.
All right. Actually, I have a small question related also to the theorem directly. So I understood from the talk that, I mean, you are basically getting the depth composition in polytime, just as you say this here too, I think, yeah. Oh no,
well, it's in FPT time.
In FPT time, of course, yeah. I mean, yeah. And then by your main theorem, this implies that there is a matrix which has a small tree depth, right?
Yes.
But somehow this was phrased existentially, but this is also constructive, right?
Yes, yes. Okay. So I didn't put everything in the theorem, but we can do all this constructively. So the main corollary of this is that we can solve any integer program which has small branch depth and small coefficients in FPT time.
I mean, yeah, that had to be the answer. It was just because in the talk it also was phrased existentially.
Oh, okay. Yes.
So I was just a little
confused. Yes. So all of this is constructive, and that's actually where most of the work is done, because it's not so difficult to prove the first point, this existential point that the branch depth is equal to the optimal tree depth. But actually, and there is an existing algorithm to compute an approximate depth decomposition, but the approximation is exponential. And so it still gives an FPT algorithm, but getting an algorithm which finds a depth decomposition of the correct depth, that's what takes most of the work.
I see. Yeah, the talk gave a very nice intro to everything and explained the surroundings very well. So this was the only one specific thing that was left open in my mind. Okay, thanks. Further questions? We would still have time for a question.
You mentioned there was something in Slack?
Yeah, but we heard the question already.
Okay,
I think it was the same question. And it was also here.
Okay.
Yeah, the chat says already asked live.
Okay, good.
Okay, thank you very much then.
Good, thank you very much.
Then we move on to Janos, I believe.
Hello.
Hello, welcome. Please give us a short reminder of your paper.
Yes, of course. Can you see my screen?
Yes, that works perfectly.
Thank you. Well, our work is our study is an FPT algorithm for recognizing k-apices of minor closed graph classes. It's a joint work with Ignatius Sau and Dimitrios Stylikos. And well, our study is in the general context of graph modification problems, where we ask to modify a graph such that the resulting graph has some desired property. The modification operations can be local modifications on graphs, while the target property usually is a graph class P characterized by structural or logical properties. And here in our study, we focus only on vertex removals as modifications. And in fact, for every fixed graph class P, we define the following problem, vertex deletion to P, where we are given a graph G and a non-negative integer K, and we ask to find a set of vertices of size at most K that when removed from G, from the input graph, leaves a graph in P, in the target class. In other words, we can see the problem as recognizing k-apices of P, that are graphs that are k vertices away from having the property P. So this problem was proved to be NP-hard for every non-trivial P, and by Lewis and Giannakakis, and we focus our study on specific graph classes that are minor closed graph classes. Well, here I give a short reminder of what is a minor. Well, a graph H is a minor of a graph G if H can be obtained from G by contracting edges in these colored bags of G. So a graph class is minor closed if for every graph in this class, every one of its minors is also in this class. And well, what we have is that for every fixed minor closed graph class P, there's an FPT algorithm, an algorithm of time f of k times a polynomial of n, solving our problem, vertex deletion to P. So for minor closed graph classes, we have an FPT algorithm for the problem. Well, this is a relatively old result, but only very recently an explicit function f was given for this problem. And in fact, in our work, we provide an algorithm for every minor closed graph class P, running in time 2 to poly k times n to the third, where poly is a polynomial whose degree depends on P. Also, in the special case that P is a minor closed graph class, excluding some apex graph as a minor, that means graphs that are one vertex away from being planar, we improve the running time of the above algorithm from n to the third to n squared. And that's it. Thank you for coming here.
Thank you very much. So I believe we have some questions in Slack, but they are also present here. So I hope we get the questions live.
Hi, I can ask my question. Also, it's a big wall of text to read up from Slack. So it's mainly aimed at improving possibly this n cubed to n squared. Now there's a trick that I learned from Mark Segan at some point, where instead of doing iterative compression for n rounds, if you have an f of k approximation to your problem and you put all those vertices last, then you only have to do f of k rounds of compression and it can save you a factor of n. So effectively the question is, do you see any way of getting, say, an FPT approximation in quadratic time? Because that I think would allow you to get rid of one factor of n.
Well, yes, that's very interesting. I mean, if we had this algorithm, this approximation algorithm, that would output a solution of, I think, a polynomial of k, of size of polynomial of k, in a very good time. I mean, a time, running time that competes with the running time of our algorithm, then yes, we could improve n cubic to n quadratic. But we are, well, I'm not aware of any algorithm like this. I mean, I think the best approximation algorithm for this problem is in the restricted case of planar graphs that I think is proved by Cavallaro-Bassi and Sidiropoulos, that only guarantees a polylogarithmic approximation. I mean, we don't have a result even for planar graphs for of constant approximation, of constant factor approximation. So I think it's if we had such an algorithm, it would be perfect. But I think now we are far away from having such an algorithm, such an approximation algorithm.
Okay, thanks. I agree that approximating planar vertex deletion is a hard problem, but I think the setting you're in is much more relaxed than the current approximation algorithm to try to target. So one, it would be sufficient to get a 2 to the poly k size solution. And two, I think it would be sufficient to get it in FPT time instead of in polynomial time. So this might be a regime that hasn't been studied yet from the approximation perspective.
Yes, yes. Yes, yes, I'm not aware of such a result, but it would be nice. I mean, it would fit our work.
Okay, thank you.
Thank you.
I also had a question. So your running time is 2 to the poly k, where the exponent of k depends on h or on the excluded minors. And do you know some cases where you can actually say what this exponent is? Like if h is somehow simple, then the exponent is at most that, or something.
Yes. Well, in fact, to be clear, the polynomial, or the degree of the polynomial on k, or the running time, as I said also in the talk, it's something that has to do with finding an homogeneous wall. So the crucial part is how big wall we need to have in order to obtain an homogeneous wall. And this is something that depends on the class. And in fact, it's something that we called palette variety of the class, of the target class. And it has to do with the number of different folios that we can route inside its flap. So if we say, for example, that the palette variety of our class is C, some constant C, then the degree of the polynomial we have is 2 times C plus 2. So yes, it depends on this C. That's the palette variety of the class. And that is equivalent to the number of different folios that we can route inside these flaps.
Mm-hmm. Okay, thanks. And so I have a minor question about your last slide where you mentioned other graph modification problems, and you said edge addition, but to me it didn't make any sense that if we are talking about a minor closed graph property, then it makes no sense to add edges, because
Yes, you're right. This was quite ambiguous there. Well, in fact, what we can't do is, well, let's say it in a different way. The removal of edges and the contraction of edges can be somehow seen as a similar operation as vertex removals. I mean, the same techniques can more or less be applied on edge removals and edge contractions. The edge additions is a completely different story. And well, we don't know how to do not only edge additions, but combinations of edge removals and edge additions, for example. I mean, we can consider a variant of the problem when we can remove edges and also add edges. And our total budget is K. But this is something that we yet don't know how to do it.
So you have to remove k edges, and you have to add k edges as well, or you can add k edges as well, because
yes, maybe considering that we have K1 removals and K2 additions.
So my point is that the property is closed under removing edges. So adding a new edge just makes it less likely to belong to the property. So why would you add an edge?
Yes, I don't know from a practical point of view, but yes, I don't know. In fact, I mean, one could consider adding edges. No, I mean, we can remove edges from a part of the graph, add them somewhere else. And why do we have a guarantee that this is it's minor free?
I mean, so in that case, it would be better just removing the edges and not adding anything.
Yes, yes. Or maybe, I don't know, considering that we have to add at least one edge.
Okay, you have to. Okay, so I mean, it's a bit of a strange problem, but then it makes sense that if you have the problem of that you have to remove k edges and you have to add k edges.
Yes, it's somehow counterintuitive. I mean, yes.
Yeah, if you consider this kind of problem, then sure, then it is a question how these techniques can be made to work for them.
Yes.
Thanks.
Okay, thank you very much for the discussion. I believe we should move on to the next paper now. So that would be Alex. Are you there? So you're welcome to share your screen now and give us a short reminder.
Yeah.
Thank you,
Melanie. Yeah, I'll give you a brief summary of our paper, Hitting Long-Directed Cycles is Fixed Parameter Tractable. This is joint work with Daniel Marx and Matthias Munich. And in this paper, we consider the directed long cycle hitting set problem. That is, you are given a directed graph and integers k and l, and you want to find a set of at most k vertices, such after the removal of those vertices, every remaining directed cycle in the graph has length at most l. And below you see an example where we remove 2 vertices, and then every remaining cycle has length at most 3. And the main result of our paper is that this problem is indeed fixed parameter tractable in the parameters k and l. We also give a single exponential algorithm in these parameters. And you can also see that none of the parameters on its own would suffice to obtain a fixed parameter tractable algorithm. And from our technique, we try to imitate a bit the directed feedback vertex set algorithm, where you want to hit all cycles by a set of vertices of size at most k by Chen et al. And the first step, like doing a disjoint iterative compression, just works. And then you have an instance where you're already given a solution of size at most k plus 1 and want to find a disjoint solution of size at most k. And then the first problems appear. So the paper by Chen et al. Critically uses that every vertex of your old solution T is on its own in its strongly connected component. And we want to have a similar property, and that's why we reduce to something we call isolating long cycle hitting set, which we obtain by just, if we can guess 2 vertices which are in the same connected component, strongly connected component after removal of the solution, we try to find a cycle or closed walk in that part and contract it. And to obtain such a closed walk, which is not intersected by our solution, we use k-representative of paths, which I will mention again in a bit. And then in the third step, we do what was yield separator in the directed feedback vertex set. And this is more technical work, which has to be done, but is maybe not as interesting as the k-representative set of paths. This k-representative set of paths is what I think is the main message of the paper, which maybe others can use. A k-representative set of paths is a set of paths between vertices t and t prime, such that for any vertex deletion set of size at most k, if there is still a T to T prime path after removal of X, there's also a path disjoint of X that already is in the pre-computed set P. And we show that for strongly connected graphs, where every cycle has length at most L, there is a bounded number, so like function of L and K times log N, number of representatives or representative set of paths of this size, which can also be constructively defined and then used for an algorithm as we do in our paper. Yeah, so short conclusion, we have shown that directed long cycling set is FPT, and we mimic somehow the algorithm for directed feedback vertex set, which has a 2 to the k log k algorithm. So I don't state the polynomial here, it's a bit ugly. So maybe we can get the runtime down to match those of directed feedback vertex set for fixed L. And as we need to detect long cycles, which takes 2 to the O of L times Boolean time, maybe we can match that runtime for fixed K.
Okay, thank you very much. So I guess, again, let's start with the questions from Slack that are also in the audience, from people that are in the audience. So,
One, two, and I'll go.
Great.
Of course, it's a big open problem in kernelization if directed feedback vertex set has a polynomial kernel in K. Now, since your problem seems to be harder than directed feedback vertex set, I was wondering if here at least you can prove superpolynomial kernel lower bounds, say parameterized by the sum of L and K. Do you know?
No, we haven't really tried. So for hardness, we just looked at, it generalizes directed feedback vertex set and Hamiltonian cycle. That's all we consider for hardness, and just focused on algorithms.
Okay, Tore?
Yeah, I just had I think I answered it myself now, but so the open question about separating the dependence on L and K, the best version you have of F, the most aggressive upper bound you can put on the F in your algorithm is L to the K squared log K, right?
Yeah, and you have
That's
some
certainly
dependency
in there,
of 2 to the L to the 6 separately. So that's not mixed, but
yeah, that's not mixed exactly.
Yeah.
Where does that come from?
I think it's essentially that we use the K representative set of paths, which I told you about, which has K squared log K in the exponent, and mix it up for
Yeah, okay. Maybe that makes sense to me. Okay, fine, good. Answered. Thank you.
Okay.
Okay, thank you very much.
Yeah.
Then I believe we have another question from Slack. I was also tempted to ask this. I wonder whether you can give some applications or potential applications of finding such long directed cycle hitting sets. So that's what Yongli asks.
So I can't give you any direct application of this, but I like to think of it as so the size of a longest cycle, called the circumference, as another parameter for directed graphs. For undirected graphs, you have often tree width as a parameter, which is really great. And for directed graphs, you have directed tree width, DAG width, Kelly width, and you don't know really which parameter to take, and sometimes they are too weak. And circumference bounds all of these 3 parameters. So maybe if you tackle some problem, you could use circumference, and then if you consider vertex deletion problems with that parameter, it can help. So the K representative set of paths can help you. And maybe you want to extend to graphs that are K vertices away from having bounded circumference. So you could use the result for that. But there's not the clear real application for that.
Okay. Now you also made the distinction between directed and undirected. So can you say a little bit more about this? So what actually happens if I just have the long cycle hitting problem and there's no directed in front?
So you could use our algorithm, replace every undirected arc by forward and backward arc, and if L is at least 2, the newly introduced cycles have length 2, and you can use our directed version. And if you also want to hit cycles of length 2 in an undirected sense, then you have parallel arcs, and then you can do some matching stuff. And if you want to hit all cycles, you can do feedback vertex in the undirected sense.
Yeah, okay. Okay, thanks. Are there further questions? No, I guess the time is already out, unless there's a short question left. That does not seem to be the case. Then we go on to the 5th paper, and Magnus should be the speaker. I think I saw you. Oh, there you are. So you're welcome to share
sorry,
your
I
screen.
was grappling with the controls.
Yeah. There's also very many videos in this session.
Okay, so sound and slides working?
It's working.
Yes.
Please do.
Right. So I'll be talking about multicut-mimicking network. So the setting is you have a large graph with a small number of terminals. Your parameter is the total number of edges on the terminals. And you're interested in preserving basically the minimum multiway cut for every partitioning of the terminals into parts. But you want a smaller network G prime on the same terminal set that preserves the same cut values. So do it a little bit more carefully. You have a graph of the terminals. For every partition of the terminals, there's a natural problem of just removing edges from the graph to hit all paths between the different blocks of the partition. The mimicking network we want has the same optimal cost value for every such partition. And our results are twofold. There's a existence result that every graph, undirected of course, there always exists a multicut mimicking network of size k to the order log k. And if the small set expansion problem had a slightly better approximation algorithm than what's currently known, then we could compute such an object or some quasi-polynomial size solution in polynomial time. The reason mainly to care about these multicut mimicking networks would be that it's the natural direction to answer the question of existence of a polynomial kernel for multiway cut. But in terms of the actual technical results of the paper, it's completely focused on the multicut mimicking network property. Questions?
Okay, thank you very much. So I believe we have 3 questions in Slack, one of which has already been answered. So Daniel, do you want to pose your questions?
Yes.
Thank you.
So maybe an obvious question is, what about directed graphs? Is there any hope for similar results in directed graphs, or what is the point where things hopelessly break down if you use directed graphs?
In terms of the proof, that's an important step that was glossed over in the video, which is that we're assuming that basically every component in the solution is something like an importance separator. So we are assuming that if you take one component and try to grow it as large as possible towards other terminals without without increasing the number of edges, then you get another optimal solution. And I think for most directed natural problems, like even directed multiway cut on 2 terminals, the greedy pushing property doesn't hold anymore. And that's definitely central in the network. If you hypothetically had some directed question where pushing is allowed, maybe it could be applied. but after thinking for a couple of minutes, I don't know if there are any applications like that.
Well, I mean, the skew separator kind of things that pushing works. So if you maybe restrict to a certain kind of multicut.
That's not is that exactly a?
Well,
I mean, okay, there's something else which goes wrong in a more subtle way in terms of the skew separator. I mean, I also know that you don't get a kernel with two-terminal skew separator. Yeah. So.
Okay, and do you have any kind of lower bounds that a mimicking network needs to have size at least this and that?
There exist strong lower bounds if your parameter was the number of terminals. There are exponential lower bounds even for cuts. And for normal cuts, like with the directed edges, I think you have a k-square lower bound. But for this actual question of undirected graph and partitions with a terminal set, I genuinely don't know. I mean, there's definitely nothing stronger than polynomial, but I don't know any reason, any lower bound.
Okay, thanks.
Okay, thank you very much. So Bart, what do we do with your question? I see it's already answered on Slack. Do the two of you want to say something about it, or?
I was happy with the answer. That's what I can say.
So we're happy with that. Are there further questions then?
I would have one.
Alex?
So there's also the parity constraint multi-way cut where you care about the parity of paths between terminals. Is there any hope that such a multi-cut mimicking network would also preserve the parities between terminal sets?
So since I haven't seen the question before, I don't know if this is the same thing, but I would say there's a couple of other problems which look more advanced but reduce back into the problem of finding a partition. For example, if you had a setting where your edges are labeled from a group and you're trying to kill all cycles that are non-identity, then under the if the approximation algorithm existed, also this group feedback edge set problem would have a quasi-polynomial kernel for any group.
Okay, thank you. I have to think about it.
What you said might be different.
Yeah, but it's a good point. Thank you.
Quick question if there's still some time. So you say if a certain approximation exists, then we get quasi-polynomial kernels. Do you know if the kernel lower bound frameworks can be pushed to exclude quasi-polynomial kernels in some cases, or do the techniques we have not reached so far?
My understanding, I mean, if we have the complexity theorists in the audience, maybe they know better. My understanding is for any regime where the lower bound applies, it almost certainly gives you implicitly a plausibly exponential lower bound. You can always imagine something where your output is almost exponentially larger than some other output or something, but a direct application, I think, would have to base on a much more contested hardness conjecture than the normal one. Okay, no, well, I mean, sorry, since we can exclude kernels of specific degree k to the c, you can probably also just use that framework to hypothetically exclude some other function, but I've never seen that used, of course.
Okay, thank you very much. Any further question? We would have 2 seconds for another question, but that does not seem to be the case. Then thank you very much. And the last paper is presented by Philip, I believe.
Yeah.
So please give us a reminder of your work.
Okay. Where is this? Okay, which one is this? Yeah. Okay. Can you see my screen? Yeah. Okay. So this work is a 2 plus epsilon factor approximation algorithm for split vertex deletion. This is joint work with Daniel Lokshnov, Pranabindu Mishra, Fahad Panolan, and Saket Sora. Now, a graph is a split graph if we can partition its vertex set into a clique and an independent set. And a split vertex deletion set of a graph is any subset of its vertices whose deletion gives us a split graph. In the problem that we are looking at, the input is a graph with vertex weights, and the goal is to find a split vertex deletion set of the graph of the smallest weight. This is known to be NP-complete even when there are no weights involved, and there is a polynomial time 5-factor approximation algorithm which works also for the weighted case. So we have 3 results. First, there is a lower bound on the polynomial time approximation factor. We show that there is no 2 minus epsilon factor approximation in polynomial time, assuming the unique games conjecture. Then we show a quasi-polynomial time approximation algorithm, which gives a factor of 2. So this matches the lower bound, except we take more time. This works also for the weighted version. And the running time is n to the order log n. Our main result is a polynomial time approximation algorithm, which gives a 2 plus epsilon factor for any fixed epsilon. So this works for the weighted version. It is randomized, and the running time is of the form n to the f of epsilon. So here are our techniques in brief. For the lower bound, we reduce from vertex cover. For the quasi-polynomial time 2-factor approximation, we make use of a result by Sigan and Pilipchuk, which says that for an n-vertex graph, there is a collection of n to the order log n, so-called clique independent set separating sets. So and that these can be enumerated in time, which is linear in the size n to the order log n. So we enumerate all these separating sets, and then we apply the well-known 2-factor approximation algorithm for vertex cover to each of these separating sets. Now, the third result, the almost the polynomial time approximation algorithm, which gives us a 2 plus epsilon factor. In this, we take this the quasi-polynomial time algorithm, but instead of going over all separating sets, we do a smart search among them and to find a correct separating set. And then we apply the 2-factor approximation algorithm for vertex cover to this separating set. So then we get the main theorem, which is that there is a randomized algorithm which, given a graph G and a weight function on the vertices and a fixed epsilon greater than 0 as input, it runs in n to the f of epsilon time and outputs a split vertex deletion set whose weight is at most 2 times 1 plus epsilon times the weight of an optimal split vertex deletion set for this graph. And this happens with probability at least half. So some open problems that we could look at is firstly to make this 2 plus epsilon to a 2-factor approximation for split vertex deletion. Another problem which is somewhat similar to split vertex deletion is cluster vertex deletion, where we are asked to find a set of vertices whose deletion will make the graph will break up the graph into a collection of cliques. So currently there is a 2.25 factor approximation algorithm known in polynomial time. The question is, can we improve this to 2? And that's the summary. Thank you.
Okay, thank you very much. Are there questions in the audience? Go ahead.
So I got some answer to my questions on Slack, but let me ask again. So my first question was about what other versions of graph modification is known to split graphs, like with edge deletions, edge contractions, and so on. And in particular, what can we say about the approximability of those versions?
So I could not find anything related to this. I did a brief search, but I don't know about known results for these.
But so I guess the 5 approximation should work for.
Let me see. So the 5 the 5 approximation works by the local ratio technique. But as far as I've seen,
okay, so yeah, with edge deletion, each of these objects has at most 5 edges that you can delete, I guess.
Yeah. There are some 3 graphs. C2, so it's like this. Yeah, then yeah. So this I'm not sure it will work for edges. But if it does, it does. Yeah.
And my second question was about yes, the application of what did Zygan and Pilipchuk use this click independent set separating collections and
so they use this to show that split vertex deletion can be solved in time is almost as good as the time for solving vertex cover times k to the order k factor. So yeah, for this they said, okay, here is a small or a like a pseudo polynomial in k set of things that you have to look at. So that's where they came up that used it.
Okay, and I have another question that can you use kernelization perhaps before in an approximation preserving way that so in principle if first you compute a kernel and then maybe use this Quasipolynomial algorithm or it doesn't matter because the parameter can be linear in the size of the graph.
That is, yeah, I've not thought about it, but right now I don't see how. So maybe to improve the running time a bit.
Yes.
Yeah, but.
Okay, yeah, thanks.
Yeah.
Okay, thank you very much. We have time for more questions. So I wasn't familiar with this problem. Can you give a motivating application to me?
I don't know of any actual applications, but this has been studied quite a bit for a long time.
Oh, I believe that totally, but I mean, it's just, I was just wondering if there's like a...
Why would someone want to split a... Yeah. This I have no idea. I'm sure if we look at some of the earlier papers, they would say, okay, it comes from this or the other one, but no.
Okay. Okay, any further questions? I believe we have discussed the questions from Slack now. So if there are no further questions, then thanks to all the speakers for the presentations and the answers, and to all the audience members for asking questions and for the lively discussion. And I guess then we can end 3 minutes early.
Melanie, thank you very much for a very well-run and stable session with good sound. This is not easy. This was really a pleasure.
Oh, that's great. But I guess the technical wonderfulity of this is due to the organizing staff. But thanks. Okay.
Oh, you chose to wear a headset, for instance, which makes a big difference.
Thank you very much.
Thanks for sharing. Bye.
Thank you.
Have a great afternoon.